Welcome to the fourth session on holomorphic functions, part of complex analysis course. Today we are going to do one of the most standard and basic results of holomorphic functions, namely Cauchy Riemann equations. This is very much needed for students because in every test there will always be questions related to Cauchy Riemann equations, either state and prove or state, and then some applications proves this function is holomorphic or not holomorphic, etc., etc. Okay, we will spend some, we will give some examples of that. Okay, we will derive, but then we are going to derive Cauchy Riemann equations in very many ways. Okay, something which is usually not done in standard courses, which will be useful. Later we will also talk about there is a fantastic geometric meaning of Cauchy Riemann equation. Okay, and that is very rarely exposed, and we will do that also. Okay, that will be second, but that's only for students who have keen interest in learning subtle aspects of mathematics. Okay, that second part many people can ignore, but that will be separate video. Okay, let's get started. The first thing I would like to talk about is the notion of, suppose f is a function from u to r, u to c, then we write as f as u plus iv. This is called the real part of f, and v is called the real imaginary part of f, right? So these are nice because we know that f of z is a complex number, therefore I can write it as x. Okay, something like real part of f of z plus imaginary part of f of z, etc. Okay, and it's a theoretically easy, but what I find is, again, in my experience, okay, many students, okay, do not know how to do that. Is just requires care and practice. Okay, so let us give some very easy examples. Okay, suppose my f of z equal to z bar, right? Therefore, what is u plus iv? And remember, this u, whenever you write u, we think of it as a function of two variables. You should write u of z plus I times v of z, f of z. But remember, z itself is x plus iy, but it's very standard to write this as u of xy plus iv of xy. Okay, so we are going to do that. Okay, so let us look at it. So this is, if z equal to x plus iy, then z bar is x minus iy. Therefore, u of xy equal to x and v of xy equal to minus y. Right? This is very simple. Okay, now let's look at another thing. F from c star to c, f of z is 1 by z. Right? This we had already done in, I don't remember where, we had done it earlier. So this I can rewrite as, okay, z bar by z into z bar. Remember, z is non-zero, therefore z bar is non-zero. This makes sense. But this fellow is z bar by mod z squared. And if I write z equal to x plus iy, then this is going to be x minus iy by x squared plus y squared. Yeah. Therefore, what is a real part? What is u of xy? U of xy is x by x squared plus y squared, and v of xy is minus y by x squared plus y squared. Yeah. And the third example, I'll give some very simple example only, do not bother very much about. Okay, suppose I give another example. Suppose, let's say 1 minus z by 1 plus z bar. Okay, so this makes sense whenever z bar plus 1 is not equal to 0. This is the domain, okay, of the function. So let's not worry about. Now how do I find it? Yeah, so again to do some algebraic manipulation. This is 1 minus z, therefore I can do it 1 plus z. This will be 1 minus z squared by the same thing, 1 plus z bar times 1 plus z, right? But this is 1 minus z squared, that's okay. And if z is x plus iy and z squared is x squared minus y squared plus 2x iy, therefore I know what this object is. And remember this, you may be tempted to expand it. 1 plus z bar is x minus iy, 1 plus z is x plus iy, etc., and multiply out. But there is a very interesting way of doing that. Suppose w is 1 plus z, this is a complex number. What is w bar? It is 1 plus this, but that is 1 plus z bar. You see that? Therefore, each is a complex conjugate of the other. Therefore, this is nothing other than modulus of 1 plus z squared. How many of you understand this? Yeah? But what is 1 plus z? 1 plus z is x plus 1 plus iy. Therefore, this we know. Therefore, this is going to be 1 minus x squared plus y squared minus 2ixy. I hope I am writing it correctly. Just make sure if I am making some mistakes. X squared y whole squared will be minus y squared. Okay, I hope I am right. And this is 1 plus x whole squared plus y squared. Yeah, therefore you know how to segregate the thing. Okay, therefore the real u of xy is going to be 1 minus x squared plus y squared by 1 plus x whole squared plus y squared, and v of xy equal to minus 2xy by the same thing, 1 plus x whole squared plus y squared. Yeah. Now let's do the last one. That's my favorite usually. Okay. Last one is, what is e power z? E power z is e power x plus iy. Again, we have done it earlier. This is e power x into cos y plus I sin y. Remember, x and y are real numbers. Therefore, this is e power x cos y plus I times e power x sin y. Therefore, u of xy is e power x cos y and v of xy is e power x sin y. Right? And the next one is e power z squared. This again is easy. We had already done e power z squared. We know that, right? X squared minus y squared plus 2i xy. Yeah. Therefore, this is e power x squared minus y squared into e power I 2xy. That is e power x squared minus y squared into cos of 2xy plus I sin 2xy. Therefore, you know what is u of xy. U of xy is going to be e power x squared minus y squared into cos 2xy, etc. Okay. So pause, review, proceed. Now let f u to c be differentiable. So what is the definition? Let's say at z. Okay. Therefore, the definitions f z plus h minus f of z by h converges to some f dash of z. Right. Now let's look at z here. Right. This is my z. Alright. Now there are two ways of approaching z. One is purely on the along this. Therefore, this is going to be z plus h, etc., where h is real. These are the points so I can approach. The other one is completely this way, and this will be z plus IH, again H is real, right? Remember, this H is supposed to be in the neighborhood. Let me just look at a picture. Either, see, this is okay. My z plus h must be somewhere here, okay, some point. You understand that? This will be some z plus h, because h is going to be somewhere here. It could be anything, but h I can go completely along the x-axis or completely along the y-axis. Instead, I can say completely along the real values or completely along the purely imaginary values. Do you understand that? So I want to look at it that way. So let h be in R. Let us look at, okay, so that z plus h belong to u, etc. Okay, f of z plus h minus f of z by h, right? Now notice that if z is x plus iy and z of h is x plus h plus iy, right? Therefore, this is something like f of x plus h plus iy minus f of x plus iy by h. So in some sense, if the limit exists, it is like something like, you can think of this as a partial derivative, dou f by dou x. Think of f as functions of x and y, two variables, then it becomes this. Do you follow that? Because we are giving the increment only in the real variable, okay, real part of the complex number, right? If you don't want, I will again, the classical books will write u f equal to u plus iv and do that. I will come to that, okay? Don't lose heart. The other way is, suppose I look at this way, f of z plus ih. Remember h again, h is in R, so that z plus ih belong to u, minus f of z by, this is again ih, because what is the increment? The increment is ih. Don't think only h, okay? This is a mistake some of you might do, right? What does this mean? This is f of x plus I times y plus h minus f of x plus iy by ih, right? Therefore, this I can think of 1 by I into f of x plus I times y plus h minus f of x plus iy by h. Again, think of f as a functions of two variables x and y, the real part of z and the imaginary part of z. Then I am giving increment where only in the imaginary variable, right? What is the increment? The imaginary variable is y. I am giving increment only h. Therefore, this fellow is 1 by I of dou f by dou a. Okay? Don't lose heart, because this is not the standard way of proving Cauchy Riemann equation. I will come to that in a minute. Okay? So but remember, f dash that exists. So no, right? And it's unique. Therefore, if I go through only by giving increments to the real variable or giving increment only to the imaginary variable, the final result by the uniqueness of the limit should be the same. Therefore, f of z must be equal to dou f by dou x, but it's also equal to 1 by I dou f by dou a. Yeah? So this is a Cauchy Riemann equation. Okay? So pause, review, proceed. The, let me again reiterate, this perhaps is not the standard way, because you would have seen Cauchy Riemann equation involving the partial derivatives u and v. We are going to get it in a minute. But for those who want to see that, that also I will do that. Okay? I am not going to leave you. But this is a modern way of looking at, so it will be easier. That's why I am doing. So let's look at. So what is the Cauchy Riemann equation? This is the first. Okay, Cauchy Riemann version 1 is, let me write, okay, dou f by dou x equal to 1 by I, or simply I times dou f by dou I, right? But remember, what is my f? F is u plus ib, right? And for this function I am giving only in taking the partial derivative in the x direction. Therefore my fx should be ux plus ivx, that is del f by del x. Do you accept it? Yeah. Yeah. What I am thinking? I am thinking of x as a function of f of x plus iy. So y variable is fixed, this is only variable, right? Therefore when I differentiate, but this is u of x plus iy plus v of x plus iy, or if you want to think of it, u of xy plus v of xy, I times v of xy, sorry. Yeah, right. Therefore this means I times ux plus ivx should be equal to, and similarly del f by del y will be uy plus I vy, uy plus I vy, vy. This is I times ux minus vx should be equal to uy plus I times vy. Yeah, and equate real and imaginary part. Then what do I get? I get, yeah, my ui equal to minus vx and ux equal to vy. Okay, so this is a second Cauchy Riemann equation. This is what you might have seen earlier. Cauchy Riemann 2 use ux equal to vy and uy equal to minus vx. Okay, pause, review, proceed. Yeah, okay. Now as I said, many of you might have seen the earlier notation. Let me do that. F of z plus h, let us assume h is real, etc., minus f of z minus h. This is going to be u of x plus hy plus I v of x plus h y minus u of xy minus I v of xy by h, right? But this fellow, I can take these two things together and these things together. Yeah, so this is going to be u of x plus y minus u of xy by h plus I times v of x plus h y. I took out, this is minus v of xy by h, right? Therefore as h goes to 0, so this goes to partial derivative del u by del x plus I times del v by del x and del y. Yeah, similarly other way around, f of z plus I h, h is again real, minus f of z by, what is the increment? I h. Remember, don't write h now. That's a mistake many of you will do, beginners. It's not that you don't know, because we always think h is an increment, we put below, right? That's why you and I might do. Okay, therefore it is u of x plus I y plus h minus plus I v x plus I y plus h minus u of xy minus I b of xy by IH. So then this again I can take 1 by I out. Therefore, what do I get? This is again u of this is u, if I want to write u of this is u of x plus h IV of y plus h and IV of xy. Right? When I write, as I said, following classical notation, I will not write u of x plus iy. I will write it only u of xy. Therefore, this becomes u of x y plus h minus u of xy by h, yeah, plus there, this 1 by I took out. This is just I times v of x y plus h minus v x y by h. So where does it go to? It goes to 1 by I, and this is uy plus I times vy. Yeah, that is going to be, you multiply by I both sides, that's going to be minus I, yeah, of uy. Are you following? 1 equal to minus 1 squared. Minus 1 squared is minus 1 into I squared. 1 I get cancelled, so you get minus I, right? U minus iy plus I vy, right? Therefore, this is going to be minus vy minus I uy. I hope I am writing minus into minus. This is plus, therefore it's plus vy into minus I vy. Yeah. Now, as usual, equate this with this. So what do you got? So I got there ux plus I vx. Yeah, ux plus I v x. This is with respect to x. Yeah, that is equal to vy minus iuy. So again equate ux equal to vy and vx equal to minus uy. So this is Cauchy Riemann equation. So make sure you understand. And as usual, ux stands for del u by del x. This is a standard notation you might have seen in two variable calculus, etc. Yeah, okay. Now there is a third version. Before that, let us just look at some simple examples, applications. This is the standard application. Okay, do you remember if we have from u to c is differentiable and f dash is 0, then we proved f is locally constant. Do you remember how we proved it? In the last lecture, the second lecture, where we used chain rule. Third lecture, we used chain rule to prove this thing. Right? Okay. But at that time, I said this proof is not found in textbooks. The use standard proof uses Cauchy Riemann equation. Let us see that. Suppose f dash is 0. What does that mean? That means, okay, but what is f dash? F dash of z, go back, we found that it is ux plus ivx is also equal to vy minus ivy. I hope I am writing it correctly, because this kind of things, yeah, right? Therefore, this means ux must be 0 and vx must be 0 and uy must be 0 and vy must be 0. Therefore, if I think of u as a function from, think of this as a R2 now, function of two variables, to R, then it's a partial derivative ux is 0 and uy is 0. So immediately we will conclude u is constant, but that's not true, right? That's the one thing which you should have learned from me. If u is connected or it's a convex set, then it is going to be convex. This means u is locally constant. And similarly, v is locally constant. And hence, u plus iv f is locally constant. Right? So if I have a real valued function f from any open set in Rn to R, if f dash is 0, okay, then all the gradients del f by del x is 0 on u. This will, okay, that will mean, okay, f is locally constant. What does it mean? On u, this may be like this. Take any open disk or open ball in the case of Rn, then on that it must be constant. Given any point, there is an open ball or open disk on which f is a constant. This I have done. Please go through it. And if you have seen my lectures on connectedness topology also, you would have learned that word. Or if you read my book on metric spaces, again the word locally constant might have been introduced to you. Okay, this is one of the standard exercise. Other standard exercises are very amusing. Okay, so let us look at f of z equal to z bar on C. Now I want to know, we know it's not differentiable, right? Let us look at this. Therefore, what is u? U of xy we know is x, and v of xy is minus y. Therefore, what is ux? Ux is 1. What is uy? It is 0. What is vx? It is 0. What is vy? Sorry. What is vx? Partial derivative? That is 0. What is partial derivative of v with respect to y? Which is minus 1. So, Cauchy, if it is differentiable, okay, Cauchy Riemann equation should hold. Right? Therefore, my ux must be equal to u. What is that? See, I don't remember. Ux equal to vy. Okay, ux equal to vy. Okay, but ux is 1, vy is minus 1. And similarly, uy must be equal to minus vx. And uy is 0, vx is 0. That's okay. Okay, therefore, Cauchy Riemann equations are not true. Hence, f is not differentiable on, on, on C. Yeah. Very amusing example which I see in many of the textbooks is the following. Okay, because remember I define exponential function only as a power series. Okay, and using that we already showed that it is differentiable. In fact, it is infinitely differentiable, right? Any power series can be differentiated term wise in its disk of convergence. This disk of convergence for this entire complex plane, therefore this is an entire function. We had already seen that. Okay, but many of the classical books, if you look at, okay, books which do not want to spend much time on exponential etc., they will define exponential of z by this part, right? This as exponential x plus iy, then they will write it x e power x cos y plus I sin y. Therefore, it is e power, okay, this is it. Therefore, what is u of xy? U of xy is e power x cos y, and v of xy is e power x sin y, right? So that's how they would have defined. Then is it okay? Now let us look at what is u of x. U of x is e power x cos y, and u of y is minus e power x sin y, and v of y is e power x cos y, and v of x e power x cos y. Huh? v of y, therefore v of x is what I want, e power x sine y, right? Therefore ux equal to vy, and you have ux equal to vy and uy equal to minus vx. So Cauchy Riemann equations are satisfied. But there is a problem. What is the problem? We have shown, okay, if f differentiable implies f satisfies CR equation. The converse we have not proved. Okay, you follow that? There are very simple examples to show that, okay, f satisfies Cauchy Riemann equation, but f is not differentiable. Okay, we will give an example. Okay, a so-called counter example. Okay, so let us look at f of z equal to, let us say, 0 if, okay, if z is either in R or it is in IR, purely imaginary, pure, otherwise 1. So what is this? I have, okay, so I have the function to be 0 here and it's always 1 here, right? Now what is del f by del x at the origin? Okay, are you following me? Now you will be wondering how to write real and imaginary part. Yeah, but just go back to the definition. My Cauchy Riemann equation was fx, yeah, equal to ifx equal to fy. This is our first Cauchy Riemann equation. Yeah, go back. I hope I am right. Yeah, I times del f by del x equal to del f by del y. Yeah, therefore at origin, if I want to do, okay, fx at origin is, I only take origin and go through it only the real variables. If I go through real variables, it's 0, therefore it's 0. And similarly fy, okay, I take this and go through only imaginary values, that's again constant 0. Therefore Cauchy Riemann equation is satisfied. Yeah, but f is not even continuous at the origin, at 0. Yeah, therefore Cauchy Riemann equation is a necessary condition but not a sufficient condition. Okay, therefore CR equation is a necessary condition. But there is a theorem which you will prove in the next lecture. This says if f from u to c satisfies CR equations and ux, uy, vx, vy are all continuous, then f is holomorphic. Okay, we still to prove this, to be proved yet. Assume that, then go back to the example e power x, e power z. Okay, we checked e power z satisfies Cauchy Riemann equation, therefore it is differentiable or analytic or holomorphic. That's the way classical books will prove e power z. Okay, right. We will come to this in the next lecture. Okay, right. There is one more thing. Now let's look at, there is another interesting way of looking at holomorphic function. This is interesting heuristic. Or intuitive. That is, see, f is a hi. The idea is if I have a function f from u, a subset of c to c, I can think of it as a function of z, f of z. Z is x plus iy, therefore I can think of as function of two variables x and y. But remember, x and y can be expressed in terms of z and z bar. Therefore, I can think of f as a function of two variables z and z bar. Right? We will look at some examples. We are going to explain how this gives you very modern way of looking at certain things. Then we are going to actually show intuitively a function f is holomorphic means f, if I express it as a function of two variables z and z bar, then f must be independent of z bar variable. And hence f of z equal to z bar, I should not expect it to be holomorphic. Similarly, I should not expect f of z equal to mod z squared to be holomorphic. Why? Mod z squared is z into z bar. Therefore, as a function of two variables, it involves z bar. Therefore, I should not expect it to be holomorphic. This kind of intuitive way will be very useful sometime. So, I will explain that idea. Right? So, if I start with f from u to c, I can think of this as a function of z, or I can think of this x plus iy, and therefore f is a function of two variables x and y. But remember, my x is z plus z bar by 2 and y is z minus z bar by 2i. Therefore, I can think of this function f of x plus iy also as a function of two variables f of z and z bar. If you think this is unnatural, let us have an analogous situation. Suppose f is a function from R2 to R, right? Then I can think of this as a function of two variables x and y, or for some reason, if I introduce polar coordinates r and theta, I can also think of this as a function of two variables r and theta. Therefore, I can talk about del f by del x, del f by del y, del f by del r, and del f by del theta. Do you understand this? Yeah. So I can do something similar. Therefore, I can think of del by del z and del by del z bar of f, where f is a function of from c to c. Okay. This is all formal. This is somewhat formal, heuristic, and intuitive way of looking. Okay. So if I want to del f by del z bar, now I can use chain rule, right? Suppose f is a function of two variables x1 and x2, but y1 y2 are also variable. Then I want to write y1 y2. Then how will I write del f by del y1? I will write as del f by del x1 and del x1 by del y1 plus del f by del x2 into del x2 by del y1. Should I write it separately? Okay. Del f by del y1, I will write as, this is your chain rule, del f by del x1 and del x1 by del y1 plus del f by del x2 and del x2 by del y1. Therefore, I have defined this, right? So let us look at, therefore del f by del z is going to be del f by del x into del x by del z plus del f by del y into del y by del z, right? But this you write it as fx. Okay, this is dx by dz. What is x? X is z plus z bar by 2. Therefore del x by del z is half. And similarly y is z plus z bar, z minus z bar by 2i. Yeah, therefore this is going to be fy into 1 by 2i. Therefore, if I take 1 by 2 as common, I have fx plus this is minus I fy, right? 1 by I is minus I. Do you accept it? Therefore, I can think of del by del z as this one, del by del x minus del by I times del by del y. Okay, pause, review, proceed. Similarly, I can look at del by del z bar of f. That is going to be del f by del x into del x by del z bar plus del f by del y into del y by del z bar. But this is fx and half, this is fy, and remember y is z bar, z minus z bar by 2i, right? Therefore, this is going to be del y by del z bar will be minus 1 by 2i, right? Minus 1 by 2i. Therefore, this is, if I again take half out, this is going to be fx, and what is minus 1 by I? Okay, minus 1 is I squared by I, therefore that I get cancelled, therefore it's I, right? I times fy, right? Therefore, I can think of del by del z bar as half of del by del x plus I del by del y. Okay, operating on a function f. Now, what is del by del z bar of f equal to 0 mean? What does this mean? This equation mean? So let us look at del f by del z bar is by definition, okay, half of fx plus ify, okay, is 0. This is if and only if fx equal to minus ify. That is if and only if I times fx equal to fy. This is if and only if CR equation, f satisfies CR. Right? You understand? Therefore, if f is holomorphic, that implies f satisfies CR. CR in the form ifx equal to fy, and this implies, okay, this is an if and only if, okay, del by del z bar is 0. Right? Now I have a function f which is a function of two variables z and z bar, and del by del z bar, that is partial derivative of f with respect to z bar is 0. What is the intuition? The intuition is f must be, as a function of two variables and z bar, it must be independent of the z bar variable. Only z variable should appear. That is the intuition. Yeah. This is just intuitive way, but it's a very nice way, because a lot of modern mathematics, especially complex analysis of variables, etc., this operator del by del z bar is known as Cauchy Riemann operator that plays an important role. Okay, and it also gives an intuition. Okay, if I think of f as a function from C to C, it's a function of z. You write it z, but then as a two variable thing I can think of as a function of two variables x and y, and hence I can think of as a function of two variables z and z bar. Then f is holomorphic implies f is independent of z bar. That's an intuition. I hope you liked it, and this may not be done, but learn these things well. As you go along, you will appreciate it better. Okay, we will meet again. Take care, stay safe. Yeah, for example, f of z equal to mod z squared, but that is z into z bar, therefore cannot be holomorphic. Right? But more generally, we will say that if f is a function from u, okay, to C, so that f of u is completely contained in R, then, and assume and f is differentiable on u or holomorphic on u, then f is a locally constant. Because what does it mean? If f is differentiable, f satisfies CR. And that means ux equal to vy and uy equal to minus vx. I hope I'm right. Okay. Now f is equal to u plus iv and v is 0. Therefore this is 0. And similarly this is 0. Therefore f is only a function of u, but you are saying ux is 0 and uy is 0. Therefore u is locally constant. Right? Okay. Please go through this example, and I'm sorry when I want to define del by del z bar, I was slightly confused about certain thing. Okay, if necessary I will repeat it in the next lecture, but the intuition still remains the same. A holomorphic function, okay, if I express it as a function of z and z bar, it should be free of z bar variable. Okay, and the last one I proved, if f is any holomorphic function which takes only real values, similarly if it takes purely imaginary values also, then it must be a constant. Yeah. Later, using open mapping theorem, we are going to prove if f is holomorphic from u to c, it takes values in some kind of arc or a continuous, some kind of a path, okay, like a parabola or an ellipse or a hyperbola, okay, in the complex plane, then also it must be a constant. But that requires a lot of work. Okay, but it just to whet your appetite, I said that. Okay, right? In some sense, one-dimensional image cannot be there unless it's a constant. Okay, constant meaning locally constant. Okay, right. Hope you enjoyed. We will meet again.